is planet loss? So this is not planet loss. This was the thing that was before planet loss. It was called marineexplorer.org. So it was a portal where you could get access and view the marine data. And it had all kinds of visualizations and had about 30 different data sets integrated into it from various different sources. So while doing that, we realized that while it looks nice, it is not a scalable solution because people need access to more data. So we decided to change our approach entirely and do basically a search engine for Earth data. So this solution currently is in private beta, so unfortunately you can't get access to it as a public service, but you can apply to the as a public beta user if you wish to do so. So here is a screenshot of the search interface. You can search for data, you get the list of results and also coverage areas on the map. So in addition to this, you get some details about when data is available, plus some metadata about it, and some data preview. So immediately then the question here is what data is it? So this is one example. This is data from GFS, the Global Forecast System. It's a model run by NOAA, which is a government organization in the United States that does lots of climate modeling and weather prediction and has lots of sensors and devices that measure things in the real world. So this is so this particular picture is in is data for absolute vorticity, which is predicted absolute vorticity at a particular point in time. So what kind of data do we have? So at the moment, we have about, actually this, well, obviously the index is growing all the time, so this slide is a little bit close right now. We have about 40 million different data sources basically indexed, and the index size is also a little bit larger than that. So these are the main data sources and main data types, data values that we have in our current search index. And of course, as we approach the public launch, then this will grow considerably. So as you can see, this is rather a lot of data. The index itself is about 50 terabytes or so. The amount of data that's actually being indexed is easily measured in petabytes. But even this is actually a very small slice of the data that is publicly available, that is being measured and computed and made freely available all over the world. So, of course, the question arises, why do you need to have the index if it's publicly available already? The problem with the data is that it's hard to access. It's in weird to find places, and scientists usually have interesting ideas about how to present their data. So yeah, we go and look at it and then index it and then provide access to it in a way that we think is rather more sane than what they teach. So yeah, but so how do we do this? So how do we index all this data? So our backend system, we use Scala. So I'll give a small overview of what is Scala. So basically Scala is a programming language that is strongly typed. By strongly typed, well, it doesn't do the full Hindley-Milner type inference, but it does local type inference. It has things like covariance and contravariance, and the type system generally works fairly well. But what's particularly interesting about it, it is in fact object-oriented and functional. So basically, it's a hybrid language, so it combines the ideas of functional programming with the ideas of object-oriented programming. And it actually compiles to Java bytecode, so it has interoperability with Java, which automatically makes available a huge number of libraries for use. Although if you are calling from functional code, then you have to make sure that, or Scala code, then you have to make sure that check for null and things like this that you have to do in Java, but you don't have to do in Scala if you use the type system correctly. So yeah, and the functional language, of course, has higher order functions and does the data types. What's another interesting thing is that that the default collections in Scala are immutable. So basically this means that once you create, for example, an immutable list, you cannot modify the content of that list anymore. Which kind of sounds weird, but actually makes many things much easier. Because essentially you don't have to worry about concurrent access anymore, because if from, let's say, from multiple threads you're accessing the same list, and if you can be sure that the list will never change, then multiple concurrent access is no problem. So, but of course you need to update the list with new items, for example. So then what you do is you essentially make a copy, and then work on the copy that includes the new item. So, but that also means that the other threads that were accessing the previous version of the list, they just see the world as they saw it as it was one step of time ago. So everything actually works really well with that. And it provides very strong meta-programming methods, which enables creation of DSLs, or domain-specific languages, within Scala itself. There are actually a very large number of these, where you can, for example, there's one for Elasticsearch, where you can essentially write into the program, search in index A for value B. This is the exact syntax, but essentially you can write fairly English-sounding sentences, and this gets turned at compile time. This gets turned into actual ASTs and then compiled into Java bytecode. So when it's done right, it works very, very well. There are obviously problems with DSLs. If you have this problem that if DSL has something missing from it, then it gets rather annoying to figure out what the internal structures are to go around the DSL. But still, it's a very nice language, because you can be very terse. So in 100 lines of code, you can do a lot of things. But of course, this does mean that the learning curve is a little bit steeper than just regular Java. But what the good part is that since it compiles to Java bytecode and runs on the JVM, then you get all the good stuff that comes with the JVM. So, and essentially, when the language was first created, it gave a very large boost to the development, because they didn't have to implement their own runtime or compile to native code. So obviously, you get all the benefits from JVM running on various architectures, various platforms. You get all the hotspot optimizations, for example, things like this. On the other hand, this of course comes with its own problems, because what the JVM essentially does, at runtime it doesn't use types, so basically everything's an object, as long as, except when it isn't. The objects don't have strongly attached types. Therefore, if you're doing type resolution at runtime, for example, in case if you have a type constructor and then you are doing the matching based on this on the type inside the type constructor, then at runtime, then you have to know that it's running on JVM and then do some trickery to make it work. So yeah. it works well when it does, and but sometimes it doesn't. So obviously everything comes with the downside. But as a whole, I might actually recommend it. It's very nice. And if you're coming from Java, then the transition can be fairly smooth because you can essentially start out writing pretty regular object-oriented code and then slowly transition over to functional stuff. Bit by bit, so that's very nice. So this is a programming language. So, but how do you make it scale? So let's say one pattern is the reactive programming model. So essentially, the reactive programming model it became popular due to the fact that processors are getting more and more parallel. The scale of data that has to handle becomes becoming larger and larger. And so, what the reactive model essentially means is that if an application is composed of different parts that communicate by message passing and are as independent as are fairly independent from each other, that it's resilient, that means it can handle failure of components within the system, and it's scalable due to the fact that those components are isolated, so you can, for example, scale each component separately, for example. Essentially what the reactive model enables are things like, for example, analytics on streams. So what you can do is you can build up the data structure that you can do fast queries on as data is streaming in to the application. There are a fair number of implementations of the reactive model, but one of the ideas that fits it best is the actor model. But what is the actor model? So it was actually invented in the 1970s or something. Nobody, almost nobody was actually using it. It was it was implemented. The most famous implementation is Erlang, which was implemented by Ericsson, who made telephone switches, and they had extremely high requirements for uptime. So I think they said that they have 7 nines of uptime or something like that. Essentially, the switches have been running for decades and never crashed, given the fact that they were implemented using Erlang and the actor model. So what does the actor model do? So the problem in highly parallel systems is, of course, the global state management. But the actor model is defined in a way that there is no global state. All the state is encapsulated in a particular actor. And so there are various ways to model, model the actors, but one example is that you would essentially have, if you have something in the physical world, then you would have in the software system an actor representing this thing, whatever the thing is. And as messages are sent to this actor, the actor updates its state. But the actor essentially has no knowledge of what's the state of other actors. So everything happens asynchronously, and the state is kept only locally inside the actor. This enables, again, it makes it much easier to reason about parallelism because you don't have to worry about global data structures so much. Well, there are exceptions, of course. And it enables scaling, horizontal scaling, because you can run the actors in separate machines and have them talk to each other, and the actors themselves don't really care because they just receive messages and don't care where the messages are coming from. So yeah, basically instead of threads, you should think of instead in terms of actors, and actors are representing constants in the world that you are modeling in your application domain. And in addition to this, there is the idea of the supervision hierarchies that are built in ways to make error handling as easy and as robust as possible. So, but this is of course all the theoretical model. So the actual system that we are using for our actor systems that do the data processing is called Akka. It works with both Scala and Java, and now they also have a version for .NET. So it is quite interoperable, and it makes remoting seamless, which means that you can, as I said, you can run actors on different machines. You can very easily scale horizontally if you are starting to run out of resources. And the reactive model fits perfectly into this. So because one of the properties of the reactive model, the resilience, means that if you start getting too much data, then you can automatically scale up. If you have an application that runs within the JVM on a number of threads, then it's fairly hard to run multiple copies of this and automatically have them talk to each other. But as an actor, you don't really know where you're running. It doesn't matter, you just receive the messages. So if you start getting too much data and your actors are taking too much processing resources, then you can just move some of the actors to another machine. And this can be accomplished quite automatically, in fact. And then distribute the load as the messages are coming in. And it fits very well with Scala because you can have message protocols that are case classes, and it works extremely well with the data types provided in the language. So the components of Akka are, there are actors, of course. Each actor has a dispatcher and a mailbox. And actors can send messages to each other. So messages can be of any type. Find your own message protocol. The mailbox is essentially the thing that receives messages, and the dispatcher is the thing that schedules actors to run on threads. Because what you can have is you can have, let's say, 10 threads configured for actors, but you can have 100 actors. So what the dispatcher then does, it decides which actor will run on which thread. And there are various configuration options, of course, for this, and there are many types of dispatchers, so you can choose the one that fits a particular problem the best. And now to the failure handling. So this is the supervision hierarchy, which basically implements the error care pattern. So in Akka, there is the root guardian, the user guardian, and the system guardian, and all the actors we define run under the user guardian. So, and actors can create other actors. So, and if an actor creates an actor, then it becomes a child of the actor that created it. And then what happens is that since you are the parent of the child actor, then it's your responsibility to make sure that you are in control of the child actor. That means that, for example, if the child actor throws an exception, then what happens to the exception is that the parent actor gets notification that the child had an error. And then there are a number of options that the parent actor can do. He can decide to restart the child. He can decide to ignore the error and propagate it afterwards. He can do a number of other things, whatever he decides to do. There is a default implementation of what to do with the default implementation to restart, which isn't always the best idea. But essentially what happens is that if the error is escalated until it reaches either the user or the system guardian, then the whole active system either restarts or shuts down. So essentially this creates a very nice tree-like structure where you can decide on a particular level what happens to the actors beneath this level. So if you structure actors correctly in the hierarchy, then it makes the error handling very logical. And it decouples it from the actual code graph. So in regular exceptions, you have to it just unwinds, the stack is unwound, and at some point in the stack you have to decide. But if the whole stack is, for example, the whole thread is running child actor, then the parent actor is never in the stack anywhere, so you cannot actually decide in the child actor what to do with the exception, so you can just propagate it to the parent. So, of course, it comes with its own problems sometimes. So, all this that I talked about, is available, and you can use it, but the plain Akka framework doesn't really do that much for you. You have to configure a lot of things. You have to know what the dispatchers do. You have to figure out how many threads you have. And of course, you also have to figure out what to do in case of what errors. But it gives you all the tools necessary to do this, but you have to use them carefully. There are scheduling. If you do get the scheduling incorrectly and tune the thread pools, in the wrong way, obviously this is also a problem with Java. You can have a cluster that's heavily underutilized because all the threads are busy waiting for I/O or whatever. Of course, you should use futures for that, but it can happen, and you have to tune the dispatcher basically to get better utilization. So in general, parallel is reasonable, which is obviously even worse case, right? But even with actors, you do have to think of the graph of messages that get sent between actors to make sure that the business logic in there is correct. So it makes it easier, but there is no silver bullet. And yeah, so since the whole thing is asynchronous, then you have to think very carefully about consistency guarantees. So for example, in our system, we have data comes in, is discovered by the crawler, and then there is the pipeline where the data goes through that basically results in an index, a search of the index of this data and other necessary information. But what happens if the original data is deleted? Right? So sometime later, the crawler crawls the site again and realizes, well, this file is gone, and cannot be accessed anymore. Then what you do? So then essentially the crawler should also delete any information that it has about this file. So, and at this point, for example, there is the case where, well, the index still contains the file because it's updated asynchronously from the crawling, but the crawler no longer has this information. So what do you do? Do you show the search result? And then when somebody looks at it, you show that, oh, this data isn't actually available anymore. So the usual solution to this is to have the system eventually consistent. And due to the asynchronicity of the model, if you require the system to be completely consistent at all times, then the whole actor model makes it a little bit more difficult to reach that. So it's sort of geared towards eventual consistency. So the thing that's also, since all the actors talk to each other with messages, the delivery guarantees the Topconf provides, and this is also pretty much part of the selecting all the specification is that all the messages are delivered at most once. This means if you have a network connection, if the actor is actually running on another machine and the network breaks, then the message will not get delivered through the actor. So in very many systems, this is actually fine. I mean, if you're doing things like clickstream analytics, very, very, very large number of clicks and happening all the time, then if you drop like a few every now and then, it doesn't matter. You're doing statistics. But in systems where you need the message to arrive, you need to have create workarounds within your own code. So usually the easiest way to do this is basically to do a periodic resend of the message until you get an acknowledgement from the actor that handles the message. And of course, this comes with the need to have the message processing be event-loaded. So essentially can be done many times over. So this work that can happen is you send the message and that arrives, but the reply doesn't arrive, so you send it again and then the actor does it again, and then maybe the reply arrives. So to get this correct requires thought. And of course, if the message is a part of a compensating or a business level transaction, then it is then you have to make sure that if something fails or the message is not delivered in the middle of the transaction, then you have to retry it. And then, but if the child actor then comes up with an exception, for example, then you have to roll back the business level transaction correctly, and or whatever is necessary in this particular case. So, as I said before, you have to very carefully think through the things that can possibly happen. I mean, Akka makes it easy to make it happen. So to send the message is extremely easy, receive a message is extremely easy, but you still have to think about the application logic and the error handling at the same time. So basically what this means is that since exceptions or failures in child actors can happen for various reasons. I mean, it can be a business reason. You can have an order to a product that's no longer available or something like that. But it can also happen because the data disconnection is not available. So, and of course, failure handling in this case needs to happen still in the same supervision hierarchy. So this sometimes requires the need to mix the different concerns together.
Can a child actor change some state in a database or something like that?
Yeah, of course.
Then there's a fail. There's a failure. Let's say I send a message to the child actor. Child actor changed some state in a database, but is unable to reply because of network connection. So now what does the parent actor do? The parent actor does not know if the message actually was delivered or if the message was acted on. So he can't send the same message again because it might then end as a incorrect state in the database because the same thing is inserted again and again.
Yeah, exactly. So that's why essentially in this model what has to happen is that the state update in the database has to be templated, which means that you can do it many times. If you do it the second time, the state will not actually change. So in this case, you have to model the data structures in a way that if you do the same action twice.
So basically, I can't have a counter.
You can, but
the counters are right.
But you need versions for that.
Sorry?
You need versions for the counter as well. You can do only transition from one state to another. It's much harder. You have to read it, then update it. It's much harder. But it's normal for asynchronous stuff to have such things.
Yes. It's just the simple counter can be very complicated in this case. Anybody have any other questions? Anytime you have anything. Yeah.
Actually, you mentioned that the actor is sometimes changing his state. That leads me to the question that are you using final state machine also? Akka's final state machine?
We are not using it, but yes, there is a state machine abstraction.
Any reason, or it seems to me that it does some work for you in this case?
I can't go too much into the details of what we do exactly, but essentially there is what we use is we use the pattern from Google's middle wheel. So essentially our actors are pretty much stateless, so we don't need to use that. So it's not exactly middle wheel, but it's sort of a hybrid thing. We can talk about it later. Yeah, any more questions?
So just in Erlang, there is is a pretty fancy feature. Is a hot code update. Are there any tricks with this framework possible in this direction?
Anybody here from zero turnaround? No. Okay. I don't use that. I don't use it extensively. I don't actually know.
You could plug in the Java machine which reloads the code on the fly. It's called Java Rebel, and it could reload classes, annotations, whatever.
And is it practically useful for production?
It's very useful for development, and they have a server Rebel too, which could to the certain extent renew the version of the production servers without discussing.
Actually, they dropped the server side, but yeah, Java Rebel is finished.
May I say something? Actually, Java naturally supports that. The class orders naturally support that. If you really want to do it, you can do it on your own. Web servers does all practically application servers that. This is natural feature supported in Java. I don't need JRebel or anything for this. You can do it straight from Java 1.1. It's there. It's always been there.
Java Rebel kind automates it.
Yeah, of course. You don't have to do anything. That's true.
So JRebel is just for development environment. It's absolutely not intended for production. And there was a tool for production that tried to do that, and it switched to doing like rolling restarts and other less dangerous things, and that's it.
They will fail.
I don't know about that, but actually there is the plain framework that also does the plain framework that's also built on, and you can integrate it with Akka, and that essentially what that does, it just creates a new class folder if you change the code. So it kind of does it, and they claim that it's suitable for production, but I haven't actually used it, so I don't know. But actually, there are a number of solutions to many of the problems that you said. So first, there is Akka clustering, which makes cluster handling supposedly easier. What they do is, basically this is a cluster membership solution. So where you have a number of nodes, and then the Akka clustering keeps a count of the nodes and has a gossip protocol to figure out when the nodes are dropped. So in actual reality, it doesn't. It has a number of problems. I mean, most of the time it works. They have this automatic downing system, so where they can automatically take the nodes out of the cluster if they fail and things like that. But even they themselves recommend doing it manually. And there are, so essentially what they should have done is they should have used Zookeeper for it, but for some reason they decided to do their own thing. There are problems with running it in production, but it does exist and they are improving it. So at one stage, at some point, you should be able to use it. And it does make running clusters much easier, and it does make scheduling messages and actors across clusters quite easy, and you can dynamically scale it and things like this. So at some stage I expect that it will be very useful. Then regarding the persistence, so they do have Akka persistence, which implements the event sourcing pattern. You can do CQRS on it. So just to explain what that means is that what it does, it persists all the messages that are sent to the actor, or all state updates are persisted, all the messages that come into the actor are persisted. And so essentially when an actor fails, then replays all the messages so the actor can restore its state. There is an option to have snapshots periodically from the actor state, because this sort of ties in with the question. Essentially, if you have a state within an actor and the actor dies, what do? How do you restore the state? So Akka persistence essentially is a solution for this. they very recently announced that it's now ready for production. We are trying to use it in a project, but haven't yet. But what? But it does sound like something that's very useful, and this is actually what I said before. So Akka, the framework itself is very low level, but then they are building abstractions like this on top of their own framework to make the common properties easier. So yeah, clustering is one, persistence is one. Then they have the Akka.io and Akka HTTP, which is for some reason called Spray, which essentially is the web framework for Akka. It's much more lightweight than the plain framework, yeah, it's so essentially, for instance, the Akka HTTP, what it does is you have an actor that receives HTTP connections, and whenever a connection is received, you can spawn a new actor that handles this connection, and in my opinion, that actually works very well. There are a number of other systems within the Akka.io framework. Yeah, and those as much as I use those, they actually work very well. And then finally, I think that I can mention is Akka Test Kit, because testing actors is actually fairly complicated because again of the lack of global state. And essentially, when you send a message, you have no idea when the message will actually get processed. Right? So what they have done is they have, in the test kit, they have implemented a couple of things. First, they have the ability to run the actor system on a single thread, so that essentially it loses asynchronicity and doesn't run asynchronously. So, of course, this works to a limited extent because if you have actors that need to work in parallel, or the actions that you're testing are if they work in parallel or not, then this doesn't work. But for simpler things, this is very good. Then they also have probes that you can insert inside between the actors inside the actor system, so you can verify whether messages are sent or not. And you have a number of methods instead of just in usual test frameworks. You have the assert that says assert this value equal to that other value. In Akka Test Kit, you can have an assert that says that, for example, in the next 10 seconds, this message will be sent. Right? So, and then, of course, it does the assert in the background, and then you can run parallel with it. So that's a rather so questions? Yeah.
It's about it is possible to deploy actors remotely. Let's say I will deploy one new implementation from class, and I want to just spread to the existing cluster.
Currently, they don't support that you have to update the jar. I think there is something in Akka cluster that at some future point might support this remote deployment, but it's not something they're actively talking about. So yeah, essentially no.
Are the Scala implementation and Java implementation completely separate, or do they use some kind of shared tools?
That's a good question.
.NET
I think that they have different DSL only, but it's implemented in Scala. I'm not 100% sure. I think that it's solved by the DSL.
The Scala and Akka company is the same, and they're kind of building it in Scala, typesafe.
Yeah.
They're building this kind of Akka in Scala.
So yeah, any more questions or?
How do the actors communicate with each other, or how do you communicate with actors? Not over HTTP, they have some binary protocol.
Well, internally, it's different whether if it's in the same JVM or if it's over a network connection.
It's over network connection.
Then they have the NETI, which they use for communications library. But the protocol itself, I'm assuming it's binary because you can define a serializer that the message is serialized with the serializer and then it's sent over the wire somehow and you don't really care.
I mean, it's not HTTP, so
You can
because of the overhead with HTTP.
I'm guessing if you really want, you can use HTTP, but their default implementation probably doesn't.
It's something better.
You can
Actually, isn't that you can have a protocol there in the beginning? By default, they give TCP and there is also UDP,
Oh, yeah.
but probably there are more protocol implementations available.
It
like
says some ACAP.TCP, but
Yeah,
what is it actually?
I have actually never looked at how the protocol looks like, so.
Does it have
So it
overhead
just
or
works.
not?
Yeah, it just works. I mean, essentially you don't care.
But inside
Yeah.
one JVM,
Inside J1 JVM, they use I can tell the implementation. Yeah, I know it. They use the queues, lock-free queues to be precise. It's on one JVM. Then I know it.
All right, I guess we have to finish
Yeah.
now.